Okay, 9:15, we should go ahead and start. So a couple of announcements, and then there'll be time for questions on the chapter 3 problem set, if there are any. Love to spend the whole hour answering questions if there are questions. And then as time allows, we will do, actually we got one last thing to do on strings, and then we'll start in on pictures. So we'll actually begin pictures today. So on the announcement front, Nick asked a question on Monday about double letters in a string. And in the interest of time, I'm actually not going to answer that question today. But what I am going to do is I'm going to make a video where I talk about that and give several examples. I was making some notes about answering your question yesterday, and then I was like, oh, and then I could do that example, and then I could do that example, and then it was like, it was going to be like the whole class. And we don't have the whole class to do what I think is a really cool thing, but not immediately necessary. So I'm going to make a video of that, and folks can catch that online. And anytime I post a video like that, you should totally feel free to ask questions about those things. Those are not meant to be somehow separate from the class. They're an additional resource. And if you've got questions about them, absolutely ask, okay? So if that's okay with you, Nick, I'm gonna actually push that off and make a video of it. Cool? And for family reasons, I'm not gonna actually be sitting out on the lawn today after class, like in theory I should, which is a bummer because it's a beautiful day and it would be nice to be sitting out there. But I've got to get home to give my wife some stuff, blah, 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 you don't care. So I will not be out on the lawn today. Sorry about that. And last announcement, Friday is, so day after tomorrow is another lab day. So we will meet online Friday instead of in this room. You can come to this room and do the lab from in this room if that makes you happy. But I won't be here in this room. I will be at home. And there'll be a lab that'll have a problem or two that'll be very similar to the chapter 3 problems that are due Friday night as well. And then a problem or two getting into pictures, sort of moving us into chapter 4. So, and you'll get, again, put into groups and sent off to fight the good fight and ask me a lot of questions. So, any questions about that sort of stuff? And are there any questions about the chapter 3 exercises that I can help with? Okay. Not seeing any online or in person, we are going to press on. But if you got questions, definitely ask, because questions are good. So there's one other, and I will repeat, we don't have time for me to lecture on all the stuff that's in the book. So, you know, when we say read chapter 3, you need to read all of chapter 3, and you should certainly ask questions about any part of chapter 3 that I don't talk about, but I'm not going to talk about all of it because I don't have time to do all of it. Like, to do all of the examples in chapter 3 in class would take us 2 weeks. And we'd never get to chapter 4, and that would make me sad. So do ask about things if I don't seem to talk about them, but we won't talk about everything. So sorry. So there is one last thing from chapter 3 I do want to talk about a little bit. And I'm going to bring up the whiteboard. Oh, it helps if I'm actually projecting. People in the room can't actually see the whiteboard. That is not helpful. Come on, there you go. You doing it? Yeah. Okay. So apologies for the confusion. But now I think we're projecting and sharing, and life is all on top of its thing. Okay, so moving over to my little tablet thing. So we've seen things like for C in string, do stuff with C. So we've seen that pattern. Okay, questions about that basic setup? For every character in the string, and then you have the colon at the end, and then the body is indented, and in the body you say whatever you need to do to C. Print it or stand it on its head or whatever needs to happen with C. Check if it's a vowel, all of that stuff. Okay? Questions about that? Now that's awesome if you want to do the same thing to all of the elements in the string without regard to their position or their order. Right? Here we're just going through them, and for each one, we're in the body of the loop, we have C. We don't know where C came from, we just know it's a character in the string. And we do something with it. But we don't know anything about, was it the beginning of the string, was it the end of the string, anything like that. And this is actually, in some sense, gets to your question about pairs of adjacent letters. Like when we're in the body here, we don't know what's before it and what's after it. So we can't answer the double letters question immediately, okay? And there are times, the double letters question being an example, where we care about where things are. It matters where something is, not just what it is, okay? That makes sense? So as an example in real life, if you have a waiting list for a class, and you've probably had the experience of, seeing waiting lists for classes, the order of a waiting list matters. If a seat opens up, the rules are the person who's first in the waiting list should get that seat, not the last person or the middle person, and certainly not everybody. Like you wouldn't want to loop through the waiting list and say, oh, everybody gets in because there's a free seat. Right? That might be really bad. Maybe the cap in the class is 16, one seat opens up, but there's 20 people on the waiting list, and now all of a sudden you got 25 people in the class, and there's only 16 stations in the art studio, the sculpture studio, as an example, right? So that's not going to work. So you care about the position, not just that something is in the list. We care about where they are in the list. Does that make sense? Questions? Good online? Okay, so there is an alternative where if we have S is Morris, here I'm going to actually write this a little more carefully because I care about the positioning. Let's say M O R R I S. Okay, so S is Morris. It turns out we can access the letters by position as well as just in the for loop, give me all the letters. And the positions are numbered 0, 1, 2, 3, 4, 5. So we start from 0. This confuses people often when they're new to computing, is that in computer science, we almost always count starting at 0 instead of at 1. And you've spent your whole life being taught to count from 1. And so this seems counterintuitive and perhaps frustrating. It turns out actually you've been lied to by adults your whole life, and you really ought to be counting from 0. And we're doing it right, and you're doing it wrong. I'm sort of joking, but only sort of. There are actually a lot of advantages to counting from 0. And we could spend a whole hour with me talking / ranting about the value of counting from 0. And I'm not going to get into that right now because I don't want to distract us. But it is useful. There's a variety of ways in which it really is helpful to count from 0. And in computer science, we almost always count from 0. And so the first character in a string is in position 0, and the next character is in position 1, and the next character is in position 2. And we can access particular characters by using this notation, S, and then a square bracket. And this is another thing in computer science, the different brackets matter. Like a round parenthesis is different from a square bracket, is different from a curly bracket, right? They're not the same thing. And in computer science, they often are used for definitely different purposes. So you got to make sure you got the right kind of bracket. So we use parentheses when we're calling a function. For example, we say f open paren x comma y comma z close paren. When we're accessing elements in a sequence, we use square brackets. Okay? Questions about that? So square bracket, let's say 4, is going to give us the character I, because 4 the character in position number 4, counting from 0, is I in this case. And so we can use this notation to get things out of a string and put things into a string. Okay? Questions about that idea before we do an example? Because I'm going to switch away from the whiteboard to Jess in a hot sec. So if you get questions about what's on the whiteboard, speak up. Okay, so I'm going to zoom away from the whiteboard. Stop sharing. And then share Jess. Okay. And resize the Jess window a little bit so the bottom's not so low. Is that? Yeah, that's a little better. Okay. So just as an example, let's actually look at S is Morris, and we can say S4 and we get I. And we can say S1 and we get O. Okay. Does that make sense? Questions about that? Now we can do things like, oh, no, can't do that. I take that back. I thought maybe I could just replace 4 with X, but apparently I'm not allowed to do that. So ignore that part. So we can get the things out, but we can't stick something in that way. In some languages you can, apparently we can't here. Okay, so now what does that mean for us in practice? Well, one thing that means is that where we had a function last 2 days ago, save, CSci 2020 0902.py. Oh, I need to not have spaces because Jess doesn't like that. And it's tiny print for my old eyes. There we go. Boom. Load. Now I can say print chars Morris. And it printed Morris. Okay. Questions about that? Now we could do the same thing using, and the square bracket notation is called indexing. So when I say by index here, that's what I'm referring to. And so 4 is the index of the character I in our string. So we're accessing the character at index or position 4. And so that's called indexing. So I could, instead of printing by for C in string, I could also say for I in, now what I kind of like here is 0, 1, 2, 3, 4, 5. Turns out this pattern of wanting to say for I in 0, 1, 2, 3, 4, 5, 0 to 10, 0 to 1,000 comes up so often that there's actually a tool that does exactly that, and it's called range. And so range gives you the values, if we come down here, range of 6 gives us a list of the values 0, 1, 2, 3, 4, 5. It goes up to, but not including the last number. So one way to think about it is give me the first n numbers starting at 0. And when n is 6, the first n numbers starting at 0 are 0, 1, 2, 3, 4, 5. Right? That gives me 6 numbers starting at 0. People often get sort of thrown by that end because, again, the counting from 0 thing is not what we're used to doing. But that's what range does for us, okay? And I can say range of 10, and I can say range of 100, right? And it does the thing. And range is actually quite flexible. I can tell it to start someplace and end someplace, and it will start at the first thing and end one before the second thing. Okay, it'll go up to, but not including the second thing. But in general, often all we need is just range of one thing. That comes up a ton. So here, that's going to give me range 0, 1, 2, 3, 4, 5. And so for each of those, I can print string I. That set I will be 0, so string I is going to be the first character in the string. And then the next time around, I is going to be 1. So we'll print the 1th character, which is O. And then it's going to be 2. We'll print the character in position 2, which is going to be R, and then R, and then I, and then S, and then we'll stop. Does that make sense? Questions? Print chars by index, Morris, and lo and behold, it works. Did the thing. Yay! Okay. Questions? Now, there's a significant issue with my definition of print chars by index. I've made an assumption in my function definition. Does anybody see what it might be? Yeah, Nick's right. So I've cooked in 6 here, and that's actually going to be a problem. If it could manifest itself in 2 ways. If I say print chars by index, and I provide a word longer than 6 characters, I only get the first 6 letters in the word. So when I did Minnesota, I just got M-I-N-N-E-S, and then it decided to stop. And it stopped because I said only print the first 6. So it did. Computers are very annoying that way. They do what we tell them to and not what we want them to. And those are often different things. So that's bad. We also are going to have problems if I try to print something shorter than 6. Oh, bad news. Okay, like it printed NIC, fine. So the first 3 were okay. Position 0 was N, position 1 was I, position 2 was C. Then it got to position 3, and it said the error was 3, sequence index out of range. The index you're using goes beyond the size of the data. For instance, you may have tried to access, position 10 when it only has 5 elements. And that's exactly what we did, right? The error that it's suggesting is exactly what we did. We tried to access something off the end of the string. So putting 6 in here, not good. What we really want, so what was special about 6 and Morris? Why did I choose 6 when I was caring about the string Morris? What? Yes, 6 was the length of the string, right? Morris had 6 characters, so I used 6 because that was the length. So what I really want here instead of 6 is I want length of this string. And there is a built-in function, len, that does exactly that. So I can say len string here, and that will do exactly what we want. Len of Nick is 3, len of Morris is 6, len of Minnesota is 9. So it does the right thing. You can give it a string and it will give you the length. So you see this pattern a lot in processing strings by index, is that for I in range len of string, that comes up a bunch because we want to take the set of legal indices is range of length of string. Okay? And so if I save that and load her up, and then if we do print chars by index, Nick, it doesn't break. Print chars by index, Minnesota, it does the whole thing, right? So now that's actually a much better solution because I haven't assumed 6 when the number of characters in the string might be more or less than 6. Okay? That was a lot of stuff. Questions about a lot of stuff? What's that? Is that what you mean? So I did my name and I did Minnesota down here in this example. We could do Morris if you want, or any other string, but those were the ones I did. Oh. Questions? Good? Everybody good online? Questions online? Okie dokie. So now, so far that really hasn't done us very much. Like that doesn't help us a lot because it doesn't do anything we couldn't have done before. Like the fact that we've got a perfectly good print chars here, it's arguably even simpler because it doesn't get into the indexing and the len and all that and range, right? If all I want to do is print the characters, I actually prefer print chars to print chars by index. I think it's simpler and easier to understand. However, as I said, there are times when you care about position. And so we have to like worry about that. And so I'm going to do an example now where we do care about position. And I'm going to write a function called checkPalindrome. And a palindrome is a string that's the same forwards and backwards. So Madam, I'm Adam is a famous one. Okay, so that's missing its punctuation marks and stuff because then it would not be a palindrome technically. Race car is another one. So those are palindromes. They read the same forwards and backwards. Does that idea make sense? And so we're going to check, given a string, we're going to print yes if the given string is a palindrome, i.e. it reads the same forwards as backwards, and no if it isn't. That's the goal here. Does that make sense? Now, I'm going to actually step away from Jess for a second and switch to the whiteboard. And I want to think about, well, what does it mean to be a palindrome? So if, let's say S is race car. And we have, let's write in the indices, 0, 1, 2, 3, 4, 5, 6. So in this example, what pairs do we have to check? What are we sort of saying, like, this needs to be equal to that if this is a palindrome?
We take the word and then reverse it and check to make sure it's equal to the input.
We could. So Yeshwant's suggesting we could take the word and reverse it and then see if the reverse version of the word equals the original version of the word. And that would be a totally great way of doing it. I'm not going to do that right now. Partly because I don't want to get into reversing, although there are many examples of reversing in the book, so we could steal one of them easily enough. But I also want us to be thinking about the positioning, and you could do reversing without actually caring about the positioning, and you could do the equality check with the strings without caring about the positioning. So I'm going to do it by just looking at this collection of letters. I'm not going to make a new word and compare those. But your suggestion, Yeshwant, is totally awesome. You can completely do it that way. I'm just not going to do it that way because I'm being difficult. So, like, the R here, what does that need to be equal to? Like, if we're looking at the string, what letter does this R need to match if it's going to be a palindrome? The first letter has to equal the last letter. So the R has to match this R here. Does that make sense? If it's going to be a palindrome, the first letter has to match the last letter. And then what about this A? What letter does it have to match? The other A, which is in position 5 here. So the letter in position 1 better match the letter in position 5. Okay? And the letter in position 2 has to match the letter in position what? 4. Okay. And then E has to match itself. Okay. So that's what I have to check. Is the first letter equal to the last letter? Is the second letter equal to the next to the last letter? Is the third letter equal to the letter 3 in from the end? Right? I need to check all those pairs. And if they're all true, yes, it's a palindrome. If any one of them is not true, it is not a palindrome. Right? Does that make sense? Questions about that? And so now the million-dollar question in some ways is, what is the relationship 0 and 6, 1 and 5, 2 and 4? Is there a pattern with those pairs? We have 0 and 6. We have 1 and 5. We have 2 and 4. If you add them up, they equal 6. And 6 was, what's 6 in relationship to race car? It's 1 less than the length. Okay, because race car actually has 7 letters in it. So it turns out these all equal 6. Variable 6. And 6 is 1 less than the length. So another way to see that is 6 is 6 minus 0. 5 is 6 minus 1. 4 is 6 minus 2. 3 is 6 minus 3. Okay? And it even continues. 2 is 6 minus 4. 1 is 6 minus 5. And 0 is 6 minus 6. So if I know I'm looking at index 0, what index do I compare it to? 6 minus 0. If I'm looking at index 2, what index do I compare it to? 6 minus 2 is 4. If I'm looking at index 3, what index do I compare it to? 6 minus 3 is 3. I compare it to itself. So I can compute what the other index is that I need to check with by doing some simple algebra, right? I've just actually done like a algebra problem from high school, right? Where I was solving for an unknown by doing some subtraction. I just didn't write X anywhere, but it's basically the same as an algebra problem from back in the day. And so given I, if you think of this as I, well, I did a terrible job there. These are the indices to compare to. And this illustrates something that I think is pretty important. There are times in computer science where to solve the problem, you need to not be typing on a computer. Sometimes you actually have to think and use your brain and not just use your hands. And this is one of those moments, like figuring out what character we have to compare to. If you've done this kind of problem a million times, you could probably just do it on the computer. But if you haven't done this kind of problem, you may need to step away from the computer and do a little thinking, right? Maybe a little math, maybe just a little planning. And so finding a piece of paper or a whiteboard or getting some sidewalk chalk and just doing it on the wall. I don't really care, right? But doing some thinking that doesn't involve just typing a lot and hoping magic happens, because that's not a great strategy. If you understand the problem well, it works. But if you don't, it can be really frustrating. And one of the things that I think can be difficult in a class like this is I have way too much experience, right? So I'm like, oh, well, you just do blah, 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 blah. And it looks really easy. And you like, oh, yeah, I see what that looks great. And then you get home and you can't do it because you haven't done this for like decades, right? I was programming when your parents were young, probably. And so, you know, I've had way too much practice to be a very good example to follow when you're like first learning it, right? So stepping away from the keyboard and taking a little time and writing stuff out can actually be super useful. So don't be shy about doing that, okay? Okay, so let's try to turn this idea into some code. And the key thing that we're going to need to capture is that the central idea is going to be that for index I, we'll compare to len s minus 1 minus I. So len s minus 1 was what gave us the 6, right? Because len of s is 7 in this example. Minus 1 gives us 6. And then we have to subtract I to go from this column to the column on the left. That's a lot. Questions before we go to the code? Going. Okay, let's do this thing. Questions online? Okay, let's do this thing. So, Share Jess. So I'm going to say for I in len range len string, okay, which we did a little earlier. That'll give me all the indices of the word. And now so we can say this char is string I. And we can say companion char is string len string -1 minus I. Okay. So this is capturing that idea from the whiteboard that for index I, the position we want to compare to is len -1 minus I. Okay. And then if this char equal companion char, I'll talk about equal in a second. Now, oh, sorry. What I really care about is if they're not equal. Oh, actually, so I think I can, the arrow keys are not where I'm used to on my keyboard at home, and so I frequently hit the wrong thing. So I think that'll work. We'll see. So if they're different, if I compare two characters that need to be the same for it to be a palindrome, but they're not. So if I look at the first character and the last character and they're not the same, what does that tell me? Is the string a palindrome or is the string not a palindrome? It's not a palindrome, right? If those characters don't match, I know it's not a palindrome. So I could say print no and return. Now, it's less clear. I think it's a little less obvious. If they are equal, what do we know? If we know that the first character equals the last character, do we know that it's a palindrome? No, why not? You got to check the other pairs, right? Some of them may or may not match up. So you don't know for sure that it is a palindrome until you've checked all of them. If a pair doesn't work, you know right away that it's not a palindrome and you can ignore the rest. But if a pair matches, that doesn't answer the question. You still got to check everybody else. It's a bit like if the question is, does everybody in the room have a nickel? I need to go around and ask everybody, do you have a nickel? Do you have a nickel? Do you have a nickel? And if Yubo says, no, I don't have a nickel, then I'm done, right? I know that it's not true that everybody has a nickel. I could quit. And I don't really care if Molly has a nickel at that point. Not to be mean to Molly, but it doesn't matter to the question. Like if Yubo has said, no, I don't got a nickel, we're done. If Yubo says he has a nickel, that doesn't end it though, right? I've got to keep checking because I need to now ask, does Molly have a nickel? And Molly says no, and then I'm done. But if Molly says yes, I'm like, well, I don't know, then I got to keep going. And I ask Darren, and Darren's got a nickel, then, we keep going. If Darren doesn't, we're finished. So in the same way, if these are not the same, then we're done. If they are the same, we've got to keep going through the whole thing. Okay? And in fact, we will have to go through the entire for loop, and only if we've gone through the entire for loop can we print yes. Okay? Now there's a couple of things here we haven't talked about. We haven't talked about the double equals, and we haven't talked about return. We've got to clean that up. First, let's talk about the double equals. I mentioned in class earlier that a single equal sign is an assignment. On the left should be a variable, and on the right should be a value, and we are assigning that value to that variable. That means we can't use single equals to check if two things are the same, like we would in a math class. So we, in fact, use two equal signs, or double equals, to check are two things the same. So this is saying this char equals companion char. That will be true if they are equal, and it will be false if they are not. Okay? And you can't use a single equal there, or things won't work. You got to have a double equals if you're comparing. Okay? And then this not here, I think, will invert that. I might have the syntax a little wrong. We'll get there in a second and find out. I have a lot of programming languages in my head, and sometimes the details blur, and I need to just try things and find out what happens. So questions about the double equals business? Then the other thing is this return. We've not seen a return sort of just floating in space like this. A return is a way of saying, we are done, leave this function. And so when I print the no here, I want to quit. I don't want to keep going. Otherwise, I might print a bunch of no's and then eventually print a yes, which would be really weird and confusing. Be like, is this a palindrome? No, 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 yes. What the hell do I do with that as an answer, right? That is not helpful. So I need to print no and quit. And the return is a way of saying the function is done, stop. Okay. And then this print yes only happens if we've made it through all of this and never left. We've never returned. Okay? And so if we get down here, it means we went through the entire string. All the pairs matched the way they were supposed to. We never had a failure, because if we'd had a failure, we would have returned. And so then we can be like, woohoo, everything matches. And we'll print yes. Okay. There's a lot there. Questions? Shall we try it and see if it works? That's always an interesting experience. Save, load, check, pal. Oh, I spelled palindrome wrong. Palindrome. Okay. Save, load, check, palindrome, race car. Yes. Check, palindrome. Nick. No. Check, palindrome. Morris. No. Check, palindrome. Morris, S-I-R-R-O-M. So I've just done Morris and reversed it and tacked it on the end to make a palindrome. So that should be yes? It is! Yes. We have written a fairly complicated function. And that needed the whole index thing. But the point of this whole palindrome business is we could not do that without the indexing because we had to compare strings in different locations or characters in different locations in the string. So you couldn't have done that with 4C in S because there'd be no good way of, you wouldn't know where C was, so you wouldn't know what character to compare it to. So we have to use the indexing to be able to do palindromes. A lot there, definitely ask. If you have questions. Any questions online? Questions in the room? Everybody's like stunned. Because it's 10 in the morning. We've just done awesome things. It's overwhelming. I understand. Okay. So that would be the end of what I was going to lecture on chapter 3. And we were going to do some chapter 4 stuff now. Are there questions about any of the chapter 3 stuff before we start some chapter 4 stuff? Going. Some more going. Gone. Okay. So I am going to go back to sharing my whiteboard. So I want to talk about pictures a little bit, because this is really important. And I'm going to make a new page here. Clean slate. Let's go to black. So let's talk about pictures for a second. So we've talked about how we represent numbers as bits. We've talked about the fact that we can represent characters as numbers, and numbers can be represented as bits. Now there's the question of how do we represent a picture, an image. And the idea here is fairly straightforward, actually. And it's probably, oh, that's a terrible straight line. You probably would have come up with something kind of similar if somebody had sort of said, quick, how might we represent pictures? So the idea is, well, I'm just clearly not good at straight lines. Oh, that's it. This looks a little more like Iowa than a rectangle, but sorry. The idea is we're going to organize an image into a two-dimensional grid of little colored squares. Okay? And so like this, let's say, do this guy. That is going to be at position X, 0, 1, 2, 3, 4, 5, and Y, 0, 1, 2, 3, 4. So that's going to be position X is 4 and Y is 2. That's going to be where that little square is in that picture. And so again, we always start counting from 0. And the top, and 0, 0 is in the top left, not the bottom left. This is another thing that tends to confuse people. All the sort of graph drawing you've probably done in your life, had 0, 0 down here. And X got bigger going to the right and Y got bigger going up. Here, 0, 0 is in the top left and Y gets bigger going down and X gets bigger going to the right. So X behaves the way you kind of expected, but Y is flipped upside down. And that's actually kind of annoying, and it's really the result of some complicated computer science history that you don't care about. But it is how it is, so we have to just deal with it, okay? So we're going to have a picture be just a set of squares, okay? And every square is going to have a color. And so if we have the square small enough and we have a big enough range of colors, we can actually represent pretty much anything that you want to represent as far as an image goes, okay? The size of the density of the squares matters, and the ability to represent a bunch of colors matters, but if you can handle both of those things, you're in good shape. And modern computers and even phones can represent very high resolution images with bazillions of colors. And so you can get really good quality imaging on pretty much any system that you are likely to ever interact with. Old people like me can remember when that wasn't true, but in your lifetime, that's not been an issue and shall not be an issue probably. So these squares are called pixels. which is sort of an abbreviation-ish for picture elements. So we represent a picture as a set of pixels, a collection of little squares. Okay? And each pixel has a color that is a combination of red, green, and blue. And you often see that as RGB. Which stands for red, green, blue. If you ever did painting as a kid, or if you do painting now, you can make, in paint land, there are primary colors, and you can mix paints and make all the different colors, okay? We're combining light, not paint. And in light land, the three primary colors are red, green, and blue, which is different than the primary colors in paint land. In paint land, a paint works by subtracting colors. So red paint works by white light hits the red paint and it absorbs everything but red. It reflects the red back, but it eats all the other colors. It absorbs them. Probably generates a very small amount of heat, depending on how much light we're talking about. And radiates that away as heat in a form that you can't see. So you see red, okay? And that's how dyes work. So like the green, the people at home can't see, but there's some green stuff on my shirt. And that green is working because the dye in the green is absorbing everything but the green, in particular this shade of green, and reflecting that light back and absorbing everything else. And that's why when you mix paints, things get darker. You end up absorbing more and more light if you mix different colors until you eventually get mud. You mix enough paint, you get sort of a dark brown, usually. It's hard to actually get a black for technical reasons, but you can get a dark brown by just mixing a bunch of paints pretty easily. We aren't mixing paint, we're projecting color. So the projector on the ceiling, which at home you can see that there is projection behind me. You can't really read it, but you can see that it's there. The projector is projecting light on the screen, and it is, if I say draw a patch in red, let's see, I think if I do this right about here, it might show up at home. No, not really. Oh well, sorry. What if I do it here? You see that? Oh yeah, there we go. So right here, oh yeah, so whatever. So this red, the projector is actually projecting red light on the screen, which is reflecting back and striking your eye. So it's not absorbing everything but red, it is actually projecting red light, okay? And if we do green, then we're projecting, oh, stop it. Computer having a fight. There we go. If I do green, now I'm projecting some green light. If I do blue, I'm projecting some blue light. I can make other colors by mixing red, green, and blue. So like a violet like this, that's going to be a combination of red and blue and probably some white. Like red and blue would give me a more purple. The fact that this is kind of a light violet to pink means there's probably more red than blue, and there's probably some extra white thrown in to make it a lighter color. So we can get colors by mixing combinations of red, green, and blue. And what we care about here is that these are numbers in the range 0 to 255. It turns out that 2 to the 8th is 256. So with 8 bits, I can make 256 patterns, which I can number 0 to 255. So this is saying we're going to use 1 byte of information, 8 bits, for each of the colors. So you sometimes see this referred to as 24-bit color. 8 bits for red, 8 bits for green, 8 bits for blue. Not that that particularly matters, but that's if you run across that terminology, that's where that comes from. We're using 1 bit, 8 bits or 1 byte for each of the 3 colors. Okay? So does that general idea make sense? A picture is a grid of squares. Every square has a color that's a combination of red, green, and blue. Oh, and 0 is like none of that color, and 255 is like full-on go team that color. So the color 25500 would be bright red, and 255 would be bright green. 255 would be all red and all blue and no green, which would be a strong purple. 000 is black, no light at all. 255 is white. Turn everything up all the way, and you get an equal mix, and you get white. Okay. So let's actually look at a picture. Stop sharing this. Share Jess. If we say P is make picture, pick a file, and I go to desktop, explore P. So this is the same tree picture that some of you might have seen. Oh, that doesn't share. I've got to, that's right, because it's a different window. Momentary pause while we share the other window. Go. Luckily, I had like confused blank stares in the room that was like, that's a song, something's up. So this should look, well, may look familiar to some of you. This was an example picture in the document about setting up Jess on your computer. And it's a picture of a dead tree in a lake with trees behind it being reflected in the water in the fall in Massachusetts. Now we can do things like zoom this. I'm going to zoom out to 500%. Now let's see, I need to, is that a little better? Yeah, okay. So when I zoom to 500%, you can see the little squares of color. Now, can you see this at home? Is this sort of working as a projection for the folks at home? Can somebody give me a wave or say something? Okay, Juan says it's good. So I'm going to take that as a win. Thank you. So we've got these blocks. These are the pixels. We blow the picture up enough, we can see the pixels. And in fact, especially if you have an older television, if you take a magnifying glass and look at the screen, you can see the pixels on the TV. Modern televisions actually have really high resolution and you need more magnification. But if you've got an old TV, like even with the naked eye, if you get up close, you can tell that it's made up of a bunch of little colored dots. But if we zoom this in, we can totally see that we've got these squares of color, okay? And if we come over here, right, we've got this huge sort of grid of color. And one of the nice things about this Explore tool is we can click on a pixel and it'll tell us where it is. Its X position is 158, its Y position is 146. And it shows us the red, the green, and the blue. So this pixel is 140 red, 139 green, and 153 blue, which means it's sort of a medium gray. The three colors are very close to equal. And when the three colors are equal, you get something on the grayscale from black to white. And they're since they're at like 150-ish, 140-ish, they're sort of mid-tone gray, okay? Whereas if I come down into this area here, now that is red 229, so a fair bit of red, right? 255 would be the maximum amount of red. Green 105 and blue 44. So some green, very little blue. And that's sort of keep darkening it up a little bit and making it a little greener. Okay. And then if I go up into this dark section, red is only 25, green is only 23, blue is 8. So that's actually a quite dark color. Just a little red, just a little green, almost no blue. Okay. So we can use this to explore the different parts of, the different parts of the image. So like here, this is a pretty green patch, a dark green patch. Actually also has a lot of red, more red than I would have expected. And then over here, we get a nice blue, right? So the blue is 209, the red and the green are in the mid hundreds, and that's to brighten it up. Like just straight blue would be a dark blue, and adding some red and green make it lighter. And we can see if we go up, which is making Y go down, if we move up, the blue is staying sort of similar, but the red and the green are going up. So they're now, green is now nearly 200, whereas when we were down a little lower, right, we were in the 170s, right, 160s. So as we go up, we're adding red and green to brighten the blue. Right, so we get a pretty bright blue. And then at some point, we're going to walk off into the dark part. So I think right here, nope, right here, there we go. So now we sort of cross from the sky, or the reflection of the sky, into the reflection of the trees, and we got a much darker color and the numbers change, right? They got lower. So this Explore tool is very nice. It lets you sort of look at different aspects of an image and see, you know, what's going on where at a level of detail that would otherwise be rather difficult. Right? So that's kind of a nifty tool. And the example that I gave you to like check things out, basically turned all the, well here, let's see if we can find it. Is that here? No, where did that go? Stop sharing. I thought I had that up. And I do, there we are, okay. So if I share that, apologies about the jumping around with the sharing. I don't know a better way to do this, but the little program that I gave you, and we'll talk more about all of this soon, but it went through, and any pixel where the red was greater than 120, it turned white. And I won't talk about how it did that, but that's what it was doing, is it's looking at the red value of the pixel, and if that's greater than or equal to 120, it turned it white. So basically it turned all the bright areas white, and any of these sort of fairly red areas got turned white because they had a fairly high amount of red. either because that was contributing to a light color in general, like on the white on the tree or the light blue here, or because we had red in the image, a significant amount of red in the image. Okay, so we've run out of time. Are there any questions in the 0 minutes that are remaining? Go to chapter 3. We will do fun stuff with pictures and things in lab on Friday, and then we'll do more stuff with pictures next week. So see everybody later. And I will not be out in the lawn because I've got to run home and do some stuff for home. So see everybody online on Friday.